Okay.
Awesome. Are we good to go?
Yes, good to go.
Oh, thank you so much, Luis. Hi, everyone. My name is Alex Morehead. I'm a Hopper Postdoctoral Fellow at Lawrence Berkeley National Lab. I'm otherwise known as Berkeley Lab, LBNL, however you want to abbreviate it. I'm in the SciData AI and Learning Systems group there, as well as the National Energy Research Scientific Computing Center, which is otherwise called NERSC, as well as at the International Computer Science Institute in Berkeley. And I'm joined today with one of my co-first authors, Rishabh Anand, who's a grad student in the School of Medicine at Yale. And we have many other joint co-first authors on the paper. This is a very collaborative work, so we're just two representatives presenting today. Unfortunately, others can't really join us, but we're happy to share what we've built together. So what we'll be presenting is a scientific foundation model for 3D molecules and materials that we call Zatom1. And we'll describe a little bit about that in the next few slides. So first, let's start off with some motivation. One trend that I and others have seen throughout science and throughout AI is that AI foundation models are just in general speeding up science. Starting back in 2020 with like the AlphaFold model from DeepMind, I think that was the first example I saw where there was a very clear demonstrable advantage of foundation models trained on scientific data that could advance scientific domains. In that case, that was biology, and in this work, we're just broadly, interested and excited about the potential of atomistic foundation models for chemistry and biology. And one of the, if you kind of, are interested in these types of models, one of the questions is how do you model those systems? Well, what granularity do you represent them at in a foundation model? And here we're going to naturally adopt the stance of looking at atoms in these atomic systems, these chemical systems. We consider them like the fundamental unit of computation. And if you have a foundation model that's trained on atoms, you hope that it can understand atomic systems to a point where it could accelerate to molecular and material science. However, to really understand those types of systems, like 3D molecules and materials, like some of the ones I'm showing here on the right-hand side, that foundation model really needs to understand the complexities of interactions and dynamics that can show up in atomic systems. So it needs to have a very nuanced understanding of the state of domain. If it doesn't have such an understanding, you can't build what's called like a universal generative or predictive algorithm. In other words, a foundation model, a true foundation model for atoms. If you had that kind of model, though, that could serve as this universal generator and screening algorithm in those domains, it would be applicable across a wide range of settings. Like, for example, energy research, drug discovery, and so on and so forth. So we're really motivated to try to design an atomic AI foundation model. Now, the question is, how do you do that? And there are, of course, many, many different ways to try to do that in the AI community. Here, we're just going to taxonomize the literature in two different ways. Thinking about, autoaggressive models, which most of us are familiar with, autoaggressive LLMs like ChatGPT and so on. They are just trained to predict the next word or token in a sequence. And so those are a very kind of motivating example, lots of progress in the literature, especially around scaling with those types of models. And then there's also bidirectional models. The most historic example would be like a BERT-style model in language modeling, but nowadays I think of these as more like diffusion models as well, more recent generative models or flow models. They also can be seen as a form of bidirectional models or masked language models in many cases, where you're corrupting individual parts of a sequence, maybe in the middle or the beginning or at the end, at any place. You're asking the model to reconstruct the sequence from those masked pieces of context. And so just shown here on the right is that those two different ways of building foundation models in the AI literature, broadly speaking. And we're going to focus on bidirectional models in this work for one specific reason, which is that we argue that atoms have no canonical ordering in general across molecules, materials, proteins, and all these other systems. There's just, in general, there are many different definitions of orderings, but they're not always internally consistent. So in general, we would like our foundation model to be not assume that there's a canonical ordering. And what's nice is these bidirectional models essentially don't make any assumptions on the ordering of your input data. They just learn rich representations from masked contexts and learn to unmask and clean up those contexts and learn good representations in the process. So we'll describe a little bit in the next few slides how we leverage this bidirectional modeling in Zatom1. Before we get to that, just understanding a little bit of the history of some foundation models that have already been built. One of those is highly relevant to this work called ADIT, or the All-Atom Diffusion Transformer. This is a generative model of 3D molecules and materials that was produced by Meta last year. And it was kind of the first work that showed that you could have a single neural network be a generative model across both molecular and material space. There's also BoltzGen, which came out late last year, which is another foundation model, but this one is for structure, prediction, and generation, broadly speaking, for biomolecules. Very interesting work where basically you can design a protein that binds any particular target, be it another protein, could be a small molecule, RNA or DNA. So it's a very flexible design toolkit and just broadly applicable across biomolecular science. And then lastly, there's ESM3, and this was kind of a motivating example where it's a protein-specific foundation model working across the three main modalities of proteins, sequences, structures, and functions, visualized here on the right. And notably, this is another bidirectional model, similar to ADIT, which is a diffusion model. ESM3 is a mass language model, which essentially discretizes and tokenizes sequence, structure, and function, and mass out any arbitrary combination of those tokens across the three modality tracks, and then during training reconstructs the original sequences of those tokens. And what you get at the end of training that model is a model that can reason across all those modalities interacting with each other. So you could condition the model on a clean sequence, in other words, a clean discrete sequence of tokens, sequence tokens, and have it predict all the structure tokens to predict a structure. In other words, you can do like structure prediction with that type of model, or maybe design a sequence given a structure, design a sequence and structure given a function, and so on and so forth. This is kind of a very flexible toolkit if you have this mass language modeling setup. So that really inspired us. Could we make something like an ESM3 for atoms, or at least take a step in that direction? And so that's what we'll talk about here. So Zatom1 was kind of our first answer to that question, like what would it actually take to build this kind of model? And so we design it in this way. It's the first foundation model of 3D molecules and materials, and I'll explain a little bit about what that means in a little bit. But it's visualized here in the top right-hand corner. This is Zatom1, where we have two different stages of training it. A pre-training stage and a fine-tuning stage, like is traditional in the machine learning literature. And the key thing about Zatom is it's working directly with molecular and material systems in their Euclidean space. So previous methods like ADIT had worked in this kind of latent representation space for molecules and materials. They argued that that would be kind of a smoother representation space to train generative models. And here in this work, we're, as far as we know, some of the first to find that you can train a model across both these modalities, both of these different chemical domains, without requiring like a pre-trained autoencoder to get latent representations. So instead, what we do is we represent molecules and materials in this unified kind of API where we have discrete atom types for both systems, 3D coordinates for molecules, and then fractional coordinates, cell lengths, and cell angles for materials. We also have like a class label that could denote it, tell the model if it's seeing a molecule or material, and then a time label basically telling the model which time step it's at, which I'll get into in a little bit what that's for. And then from there, the model basically performs relatively simple input embeddings, like linear projections and positional encoding standard in the ML literature. And then from there, we have a relatively standardized transformer trunk that takes all those embeddings, or it takes the input embeddings and learns rich latent trunk embeddings from those. And then from those kind of trunk embeddings, we have basically simple linear or something like that kind of readouts for each generative head. So we can predict new atom types, 3D coordinates, or fractional coordinates. So kind of the workflow of this model is we'll corrupt each of those input modalities, like atom types and coordinates, depending on whether they're discrete or continuous values. We'll corrupt those and then have the model predict back the clean version. And that's a way of pre-training this model with what we call multimodal flow matching. So I'll describe what flow matching is in a little bit, but high level, it's a generative modeling technique that's essentially applicable across many different types of modalities. So you can use it for discrete data, continuous data, and so on. And we argue that this is a very kind of tractable training objective, and it's also a good way of initializing the embeddings of our transformer trunk for downstream tasks. So once we do that, once we pre-train our generative flow model across all these modalities of data, it can now generate new molecules and materials from scratch, visualized here on the right. And it can also, shown in the bottom half part of this figure, we can fine tune those representations we get from the transformer trunk, pre-trained with flow matching for related tasks like property prediction, energy and force prediction, and so on and so forth by just adding some task-specific heads on top of the model. And so these outputs can be scalar values like your rotation invariant scalars or equivariant vector features, as we'll describe in a little bit. And then just touching on what is that flow matching I was talking about. So high level, it's a tractable way of training normalizing flows, where essentially you have two different data distributions, a noise data distribution called X0 and a clean data distribution called X1. And essentially, you can most of the time, easily sample from your noise distribution, like a Gaussian, very quickly and tractably. And your model basically learns to interpolate between these two distributions, the noise distribution and the clean data distribution. And we always have our clean data distribution because that's some real data set of molecules and materials. So we're training our model to take something easily obtainable like Gaussian noise and transform it into the clean modalities that constitute a molecular material. So the coordinates, the atom types, and so on and so forth. And so that's essentially how we pre-train the Zatom1 model with this multimodal flow matching setup. Now, this is only possible if you have access to high quality data. Training any foundation model requires a lot of good data, and fortunately, a lot of great data sets have come online over the last several years for molecules and materials. So we kind of split this up into two different sets of experiments. So we have our generative experiments for pre-training the model. So we use a variety. We have QM9 for small molecules, MP20 for materials. We also use GM drugs for molecules, which is a larger data set, bigger than QM9 with more complex examples in it. And then we also have experiments pre-training on a collection of metal organic frameworks from this data set called QMOF. And we pre-train this model in different groups, different experiments in different settings, but we'll get into those details in a little bit. Once we pre-train the model, typically with QM9 and MP20 as a baseline, then we can fine-tune it on data sets with, for example, property prediction labels. So QM9, for example, we have access to 19 property labels calculated with MD for each of the molecules. So we can basically fine-tune some additional property prediction heads coming off of Zatom's trunk and try to predict properties out of the model. We can also do material property prediction with this data set called MatBench, where there's 9 property prediction tasks available in that data set. So we've just described some property prediction tasks that we can fine-tune our model for. We can also make it a machine learning interatomic potential, or MLIP, if we have access to energy and force labels, which we do, thankfully, with these new data sets like OMAL25 for Meta and MP trajectory for materials, which contain energy and force labels for molecules and materials, respectively. One thing to note is that OMAL25 and MP trajectory, these are in general data sets that are much larger than any of the other data sets, and they also contain much larger examples in them, much larger molecules and much larger materials. So definitely a distribution shift between QM9 and OMAL25, for example. In fact, OMAL25 typically contains a lot of examples that QM9 does. So it's basically, we're going from smallest data sets to largest data sets here. Now let's describe a little bit about the generative modeling experiments. In other words, how well can we pre-train our model with generative modeling? And the way we assess that is by looking kind of through the standard generative modeling literature for molecules, and we just compare our method to existing generative models for molecules. And what we find is that if we pre-train Zatom1 in this way, we achieve state-of-the-art small molecule generation results. So in other words, we're hitting state-of-the-art just by pre-training the model. So in this example, we're pre-training on QM9 and this other data set called MP20 I mentioned before, but we'll describe a little bit more in detail what that's doing. So in this QM9 setup, we're drawing 10,000 samples or 10,000 new molecules from the model, having it generate all of those. And we're measuring, shown here in the top right-hand panel for table A, essentially a series of different unit tests you can run each of the generated molecules through. So there's this tool, really nice tool called PoseBusters, that you can basically will give you a readout, a binary yes or no, on if that molecule passes all these tests. For example, are all the atoms in the molecule connected? Are all the bond angles and links kind of in a regular range of what you would expect? No steric clashes, and so on and so forth. And you can just measure the percentage of molecules that passed all these tests. And what you'll see is that Zatom1 is hitting a nearly 100%, like almost a perfect chemical and structural validity rate across, an intersection of all of these different unit tests, which is kind of a good sanity check to see if your model has really captured the data distribution well. And even compared to ADIT, we're better in that setup, even though we have the exact same training setup and protocols. And what's nice too is we have this ablation similar to ADIT where we train the model just on QM9, just small molecules, and we see actually worse results than when we jointly train it on MP20, which is a data set I'll describe next, which is a data set of materials as well. What this means is that we're seeing positive transfer learning between molecule and material data. So in other words, training on both types of data allows us to get better molecule generation performance. So the materials are actually helping the model here, which is interesting. And then, so that was kind of the first signs of hope. We saw that we were able to kind of reproduce this phenomenon that a paper like ADIT had shown, where they had a similar setup. Training on just molecules alone is worse than training on both molecules and materials in this setup. And then we extend that, so we train on more complex molecules as well as MP20 with materials. So now we're training on GM drugs, which is a much larger data set with more chemical diversity. I'm drawing 10,000 samples from the model, and we're basically able to, for the first time, match the statistics of this data set, where GM drugs itself has about a 94% PoseBusters validity rate on average, and we're able to match the statistics perfectly, even outperforming methods like ADIT and another recent baseline called Tabasco. And what's nice is, as I alluded to, because we train this model on this MP20 materials data set at the same time, it can also generate materials. So we'll describe that in the next slide. Yes, so for materials generation, this is the same kind of setup. We are, by default, pre-training the model on QM9, which contains small molecules. And here we're going to discuss how it works for materials generation. So here, describing the data set, we're using MP20 for materials, where once the model is trained or generatively pre-trained, we sample 2,500 samples from it. And we measure its performance using this new benchmark called LeMat-GenBench. And basically what we're doing is we're assessing its performance, the generation of quality of all the generated materials across a range of different standardized metrics. And there's different categories. Kind of here, we're focusing on stability and metastability to start. And what we see is that Zatom1 can generate a reasonable percentage of stable, unique, and novel materials, abbreviated SUN, and metastable, unique, and novel materials. Basically meaning that the model is able to sample from its learned distribution and uncover materials that don't exist in well-known training data, existing training data sets, and they're also thermodynamically stable. They have low energies. And we also see, kind of with the same ablation we did in the last slide for molecule generation, if we just train our Zatom1 model on materials alone in MP20, we get worse materials generation results than when we train on both molecules and materials using this LeMat-GenBench setup. We have 3 different sizes of Zatom in this table. We have the default model size, which is about 80 million parameters, and we have different scales of that. So 160 million, 300 million parameters, and we see that there's kind of a sweet spot with our 160 million parameter model, where essentially we're able to generate very low energy structures, and we're also able to basically optimize our stability and metastability rates for materials discovery. However, one caveat to keep in mind here is you probably notice is the novelty rates of Zatom are relatively low, which kind of suggests the model is doing a lot of overfitting on materials. In kind of post-hoc studies, we've seen why this might be the case. And it's generally that learning, when we're doing this generative pre-training of molecules take quite a lot of time to get the structural details kind of perfect, as you were seeing in the last slide. But materials seem to be learned relatively quickly. And there's a plausible reason for that, which is that, MP20 is about 40,000 or so examples of materials, and it's about 3 times smaller than QM9. So it's relatively easy for the model to overfit to a materials data set that's smaller than the other molecule data set that you're pre-training on. So we're kind of seeing signs of that here, is that the model is doing basically a lot of overfitting when we're trying to maximize the molecule generation performance. So one thing that we're interested in studying in kind of future work is just basically optimizing the training time for materials to see if we can achieve better novelty rates by cutting off training earlier and sacrificing maybe some molecule generation performance. But overall, we see that Zatom1 in this current state, despite the low novelty rates, is still capable of generating metastable, unique, and novel materials, and as well as a handful of stable, unique, and novel materials, which we think are pretty exciting results. So that's just finishing up.
Sorry, Alex, I think Ali has a question.
Oh, go for it.
Very quick question. So if I understand correctly here, like training only on MP20, you get worse results than training with molecules.
Right.
And you think that you overfit more when you add on materials when you add molecules. But my question is, like, for example, for the novelty rate, it looks like you have higher novelty when you train only on MP20 for generating materials versus adding molecules. Do you have a hypothesis on why this is happening?
Yeah, so the reason is because training converges faster. When you're training just on MP20, we only need to complete about a quarter of the normal training epochs we would need if we were trying to train on molecules at the same time. So for reference, we typically train our default setup is to train for 2,000 training epochs on MP20 and QM9. And when you train on MP20, the model's basically plateaued and completely converged at epoch 500, so like a quarter of the normal training length. That naturally will mean the model has less time to overfit and give you a higher novelty rate. But what we see is basically when you actually sample from the model and run it through LeMat-GenBench, you get worse MSUN and SUN results than if you actually let it overfit more. but it's kind of counterintuitive. You drop the novelty rates, but your msoon and soon rates actually improve when you like run it for longer. So that's kind of the intuition, is that the convergence is a lot faster on MP20 alone.
Makes sense. So it's still like the overfitting argument as well. And I have a question as well, maybe a bit more basic. How do you use this model to generate materials? Like, how do you decide if you're generating a material or a molecule, for instance, when you run it?
Yeah, great question. Maybe I'll go back to the intro slide. Yeah, so the idea is that you have to condition the model. So there's this class label for Zatom, similar to ADIT, where you give it like a binary label of saying this is either a class label corresponding to a molecule or a class label corresponding to a material. So it's a flag that the model sees, and it can embed that information. And then from there, what you do is you pay attention to which modalities it's generating. So it has access to fractional coordinates, cell lengths, and cell angles, and atom types. So what we'll do is we'll randomly initialize each of those, like a random sequence of atom types, random Gaussian fractional coordinates, and cell lengths and angles, and have it denoise those for however many flow matching steps it's going to do, maybe by default like 50 or 100 steps. And at the end of that, you'll just read out those modalities that pertain specifically to materials. So in this case, that's atom types, fractional coordinates, cell lengths, and angles. And then we'll construct a material using PyMatGen. So that's essentially how we're doing it, is we're explicitly telling it to generate a material, and then we're just reading out this modality specific to materials.
Very clear. Thank you.
Yep. All right. Any other questions so far?
All good.
All right. Just stop me if you have any. Awesome. So that describes our molecule and material generation results, kind of baseline results for pre-training. And then now I'll describe some more complex materials that we've tried pre-training with a generative step, like in a generative fashion using Zatom1. So this is for generating metal organic frameworks, otherwise called MOFs. Here we pre-train on this data set called QMOF 150, which is just QMOF, the data sets filter to only metal organic frameworks with 150 or less atoms or fewer atoms. And what we find is we compare, specifically to this ADIT model that was also trained just on QMOF, and it achieves about a 15% validity rate. What does that mean? It means if you generate 1,000 metal organic frameworks from this model trained on a data set of MOFs, and you measure kind of these unit tests, how many of the generated MOFs pass all these tests simultaneously, we're left with a rate of about 15%. And we're able to match those results of ADITs here. Basically, what this is it's a test that our model has rich geometric expressiveness of materials. In other words, it can learn very complex, very large chemical and material systems that are kind of quite different from what you might see in MP20 or QM9, which are a little bit simpler test cases. These metal organic frameworks are just much, much harder to learn. And you see that reflected in the time it takes to train the model. So we'll note that time it takes to train this model to convergence is much higher than it would be for QMOF or for MP20 and QM9, the experiments we just described previously. It might take 3 times longer to converge, for example. And in fact, the authors of ADIT, if I recall correctly, they hadn't even finished training their model. And we're kind of in the same case here. Our model continues to improve as it trains for longer, but at some point we have to cut off training just for how expensive it is. But yes, that's a sign that the kind of representations of materials that we have underlying Zatom it's powerful enough to generate these complex metal organic framework systems, which is kind of exciting. And then I'll describe, this is the last section I'll describe and be covering, and then Rishabh will take it over from here. But this is our last set of generative modeling experiments, and this isn't in the preprint yet, but just some early results that we're looking at, where we, for the first time, are interested in generating molecules by training on this OMAL25 data set, this really valuable, large, and high-quality data set from Meta that was released last year. What's really interesting about OMAL25 is that not only is it large and have a lot of chemical diversity, covering small molecule space and even protein and RNA space, but also the molecules are not strictly in equilibrium. There's actually a lot of non-equilibrium structures in them in that data set. So we're interested to see if we can just take our exact same formula for training Zatom1 and just apply it directly to OMAL25 and use the exact same metrics to see how well it does. So what we're seeing here is just out of the box, if we train our model for a certain number of epochs, about 40 here, we're able to already hit about a 15% PoseBusters validity rate, meaning out of the 16,000 molecules we're generating from this model, or generating with this model, about 15% of those are passing all of PoseBusters unit tests. And there's really no baseline to compare to here, since nobody has tried training a generative model on OMAL before. So we're not even really sure what the maximum possible PoseBusters score could be. Somebody would need to actually run PoseBusters on the whole OMAL 25 data set, and possibly even need to adjust the software to tune its parameters, like its bond length and angle distribution, so that it doesn't accidentally flag valid molecules as invalid and so on. So we don't really know what the upper bound, the highest value you could get for the PoseBusters rate is, but here nonetheless we're just interested in trying the model out to see how well it works out of the box. And so we visualized here, and we were kind of seeing visual confirmation that training on this OMAL 25 data set means you're sampling much more, I would say, just chemically interesting molecules than what we'd see if you train on QM9 or GM drugs even. We're seeing like a lot more, expressiveness and exploration of chemical space, choosing rare elements to design molecules with, but they're considered, valid according to a variety of different test suites. So this is really kind of exciting. It means there's a lot of potential value by like future models, pre-training and training generative models on OMAL 25. And so we're really excited to see what kind of results come from that. But the little caveat here is that we're not done training. We know these are kind of partial results of training Zatom1, and we continue to train it, but model performance keeps improving. So we don't really know when it'll be done, but essentially it just takes a lot of time to train on this data set because of how large and complex it is. So these aren't the final results. The model hasn't finished converging. And with that, kind of concludes the generative modeling pre-training section of this paper. So the rest of the sections, Rishabh will take over and focus on kind of the fine-tuning tasks. Now that we've pre-trained our model, in this case, we can assume we've pre-trained it on QM9 and MP20 for molecules and materials. And so now what kind of fine-tuning tasks can we do with that? So take it away, Rishabh.
Sure. Can I share the screen on my end? All right. Screen. Is this visible? Hold on. Yeah, should be visible, right?
No. Oh, now it's loading. Yeah, all good.
Okay, got it. All right. Thank you, Alex. Yeah, so I think now that we have a fully pre-trained generative base model, something that's really cool and interesting is what if we could use that as an embedding model as well for downstream prediction tasks of interest. So we put that to the test, and we took the base pre-trained model, froze it, and we added a few more very similar layers from our transformer trunk, just based on this pure transformer architecture. And we did some fine-tuning on some of these benchmark data sets, like QM9. So when we look at QM9 itself, there's about 12 plus properties of interest. And when we do multitask prediction, where we predict all 12 plus properties at the same time, we essentially set the new state of the art in such a regime, compared to some of these existing methods like adaptive intervention, where they do some sort of gradient-based optimization to ensure downstream prediction. We are outperforming them by about 60%, which is good to see. Again, as has sort of been the theme, the broad theme for the presentation so far, jointly training on both materials and molecules definitely helps. So when you take this pre-trained model, fine-tune it on both materials and molecules, you can basically do zero-shot prediction out of the box. Now, when you have this MatBench data set, which is a very similar setup where you're doing property prediction of around 9 properties for materials, supervised fine-tuning again gets you very similar gains compared to very bespoke methods trained to classify on only molecules or only materials. And over here, when we have these results with a slash, the left corresponds to results on QM9 and the right corresponds to results on MatBench, especially for this homo-lumo gap property, delta epsilon over here. And over here, when you train an only molecule model, you're able to get some pretty good performance, but you can really exceed that further by, again, jointly training on both types of atomic sources. Something again that's of interest again to the community is how can you build really good interatomic potentials, which can potentially be used in molecular force fields or MD simulations downstream. And again, we have some pretty interesting and promising results. I wouldn't say it's entirely state of the art, but it sort of gives you a good base to kick off from to build MLIPs. So you take data sets like OMOL and MP-Traj, and when you are doing MLIP tasks on them, which is essentially a force and energy prediction task, and over here we do direct force prediction. We don't use autograd. We see some pretty good results on force ME compared to some of these state-of-the-art methods like ORB. And I wouldn't say they are state-of-the-art, but they are in the ballpark, sort of same order of magnitude around there, which is a promising sight. We want to sort of present these results sort of candidly, because when you look at energy prediction performance, we've trained on small molecules or small systems, but OMOL and MP-Traj they contain much larger systems. So simply because of that size discrepancy, we may be sort of entering slightly OOD territory, which explains why some of these energy MAE values are much higher than some of these state-of-the-art results. So larger the system size, you need to sum up the individual atomic energies to get the system energy, and that sort of results in a really high error. And that is something that we're further studying at the moment. Hi, yes, Ali.
Yeah, very quick question. I see that in, for example, the force field tasks, you add way more parameters than you have in the base model.
Yep.
And in the other tasks, you add way less. Is there a reason?
So again, this goes down to sort of trying to take the base model, which sort of remains at 80 million parameters, and trying to see how much extra fine-tuning you'd need to do to the overall setup to perform well on these tasks. You could take the original model and continue fine-tuning it further rather than freezing it. As for the discrepancy in like this sort of the regression head, this was based on quite a bit of hyperparameter tuning. So all of this is sort of empirically driven, just to see the extent of this transfer learning that happens between generative pre-training and downstream prediction performance.
And I'll add on top of that to your question, Ollie. The main reason is like you could do with a lot fewer parameters just for energy and force prediction. It'll just affect how long it takes to converge. So the reason we use like 220 million parameters for this task is it just made convergence way faster. And we have it's relatively expensive to train on these data sets. Like they're fairly large, like 6 million examples, and our input padding scheme is not highly efficient yet. And so it was takes like several days to get these results. And so we wanted to make sure training converges with as fast as possible. And so increasing the parameter count was the simplest way to do that. However, in theory, if you had more time or had more efficient training setups, you could just do with a lot fewer parameters and wait for it to converge.
And have you tried, so you talked about unfreezing the backbone. Have you tried doing that and see if that gives better performance or worse? Or is it necessary to keep it frozen to keep like the pre-training representations?
Yeah, it's a great question. So in this, this isn't in the preprint as well. This is another new result that you just talked about, which is this middle row under the OMOL section, where if you pre-train OMOL or Zatom1 on OMOL 25 as an MLIP, meaning you pre-train the whole trunk that I described and the energy and force prediction specific heads, that's the 93 million parameter baseline. That will give you better energy results. And this kind of goes to what Rishabh was saying about this OOD thing, where if you pre-train the whole trunk on QM9 and MP20, those are very small systems, and energy is largely a function of the size of the system. So then if you fine-tune it later and freeze the trunk and fine-tune it on some larger systems, in some sense, it's kind of like LLMs. It doesn't know how to count beyond, say, 20 atoms, which MP20 maxed out at. So it's basically a very hard task to do. And what we see is if you instead pre-train the whole trunk on these large systems like OMOL, then that problem largely starts to vanish. So it can actually count and see like much larger systems. It knows how to predict energies much better. So this confirms that in future versions of Zatom, if we pre-train on OMOL 25 and larger systems up front, then we would actually be able to balance energy and force predictions pretty well, because then the models actually knows how to basically count how many atoms are in these large and small systems. Yeah.
So if I understand correctly, if you pre-trained on non-equilibrium structures, which are OMOL, then you can unfreeze the model and you get better performance as an MLIP, essentially, because you have molecules that are kind of on the same distribution as the one you fine-tune on.
Yeah, I'm not sure I would phrase it as like equilibrium versus non-equilibrium. I think of it more in terms of the size of the systems themselves, like how many atoms are in them. So QM9 and MP20 are equilibrium structures that are very small, versus OMAL25 structures and other data sets, they're much larger on average, or at least they can be. And so there's a huge distribution shift between our pre-training setup, which we followed to kind of match, all the benchmarking conventions in the literature, so we could compare to methods like ADIT. We kind of had to adopt that setup so that we could then try these fine-tuning experiments. But the downside is then we have this distribution shift. So kind of this naturally suggests in the follow-up work, we want to pre-train the trunk itself on OMAL25 and similar data sets, so that then when we fine-tune, we have less of this distribution shift, especially for energy prediction.
Right, makes sense.
Yeah, something that we're pretty excited about potentially trying is, I think at least in the vision literature, there's all of this chatter about REPA and how can you take a base pre-trained model and sort of refine its internal representations using a really strong embedding or encoder model. I think one can envision doing a very similar setup where you have Zatom as this pre-trained base, and maybe you could sort of refine its internal representations with something like MACE. That's a really good MLIP. And maybe that's how you could sort of unlock some new gains on like this OMAL frontier at least. Yeah. Yeah, so I think maybe we can move on. Yeah, so when we sort of benchmark Zatom's speed compared to some of these existing methods, the data sets are getting bigger. I think sort of the cost of compute is, it's always been sort of high. How can we sort of ensure that Zatom is doing fast training and fast inference? So something interesting that's been happening in the NLP community for a while now is people are really excited about scaling laws. And that is something that we are also studying for Zatom. And when you have such a model which has this pure transformer-based trunk, which is sort of leveraging some of the advancements in optimizing for hardware usage, GPU usage, on QM9 and MP20, it's really cool to see that our largest version of Zatom is actually much faster than the smallest version of ADIT. And ADIT is a latent generative model, and I guess the promise of latent generation was to sort of speed up compared to latent sort of generative models in ambient Euclidean space, for example. So this is a really interesting result. And compared to some of these equivariant methods that we've seen come out, Zatom is also much faster than them. And the same can be said for using a very similar setup for geom drugs, where our largest version of Zatom is also faster than the largest version of ADIT in a very similar compute and data regime. I was mentioning scaling laws, and that is something that we have done some very preliminary investigation on over here. For QM9 and MP20, it's really nice to see that as you sort of scale up model size while keeping compute and data constant, your performance increases, your validity rate also sort of moderately increases, and something that the scaling laws literature does is sort of look at losses, validation losses. And when we look at such quantities or metrics, they are going down or converging faster the more or the bigger your model is. And again, that goes back to sort of the gains that we're getting using a very simple transformer trunk that's been very optimized for such high throughput training. Something that we've also explored is, what does equivariance or approximate equivariance bring to the table? So very recently, the Platonic transformer architecture came out, which was essentially one of the fastest equivariant models out there. And when we sort of take this Platonic block and replace it within this transformer trunk, we're able to see some much faster convergence in small data regimes, especially on QM9. And we are also trying to see if we can sort of really push that boundary to really make a case for approximate equivariance or symmetry breaking. I think Aditi Krishnapriyan's group at Berkeley is doing some really good work in these sort of hybrid setups where you have a bunch of equivariant and non-equivariant components interacting with each other. And using that as precedent, we're able to sort of make very similar claims in our case on this sort of downstream generation task, even when you look at things like PoseBusters, for example. And the Platonic transformer architecture, it is approximately O3 equivariant and comes in various settings, which we're also currently ablating. So I think with that, we've sort of covered some really fun results for generation, as well as how you can take a generative model and repurpose it for downstream prediction tasks of interest. So I think I'd like to sort of end off this presentation with some takeaways or insights that we've gotten from the paper and sort of the experience putting this together, as well as some future thoughts on what's to come. So Zatom1, again, to reiterate, it sets the new state-of-the-art for 3D molecule generation on QM9 and John drugs, as well as multitask molecular property prediction like on QM9-like datasets. We have achieved some pretty competitive performance on materials generation using datasets like MP20, and all of this put together, the team's really pushing OMOL generation, which is something that is very exciting to the community. The architecture, I would say, is one of the main bonuses of such a setup. I think the community has sort of put out a lot of really good data, and to be able to really squeeze the juice out of it, you need models that are trainable at really high throughput. NVIDIA GTC is happening this week, and there's a lot of really fun stuff that's come out when it comes to optimizing transformer performance for LLM training. What would that look like when you sort of port it over to the molecular space? And that's exactly the kind of stuff that you see in faster training, faster inference, being able to study the scaling laws on such a pipeline. Something to look forward to. I think we are very busy at work building the next sort of iterations of Zatom on new modalities. What does it mean to take Zatom and train it on proteins or very niche biomolecules like RNA and DNA, protein ligand complexes, or just complex data in general? What would tokenization look like? These are all questions that we are very interested in. And flow matching has also become very mature over the past few years. What does it look like to take more scalable, efficient versions of flow matching? There's all of this chatter in the vision literature about one-step or few-step flows, like mean flows, alpha flows. Could we take that and make it stable and less brittle in such a molecular setup where you have way more degrees of freedom when placing these atomic entities? Something that's not on the slide that we are also interested in is there's a lot of excitement over interpretability, or so-called mechanistic interpretability of transformer-based or LLM-based architectures, or pro-LLM architectures. Could we use such intervention methods to steer Zatom towards more desirable areas of molecular space or chemical space? What would that look like? Are we able to do this sort of representational alignment style frameworks? Could we use them in Zatom? And with that sort of brings us to the end of the presentation. Thank you so much for joining. I think this entire project, it was this sort of huge team coming together to make it possible from across different institutions. I think at some point in time, there was a call where we were discussing stuff and we had to collaborate over 4 time zones, which was really cool. And we are very interested in collaborations in terms of helping with scaling these approaches, building better iterations of Zatom, thinking of new ways to tokenize and interpret these models. So if any of these kind of questions interest you, we'd love to chat. Yeah, and with that, thank you so much for your attention.
Thank you so much, both of you. There's a question in the Q&A. I think you briefly touched on it, but if you can again answer, do you quantify or ablate the gains of doing pre-training with your multimodal flow matching approach versus like training directly the same architecture but like on forces and energies? And this was back to like the OMOL results that you showed.
Yeah, let me just go back to that. Yeah.
I think it's right there, that middle row in OMOL 25, where basically we see benefits from pre-training with that multimodal flow matching for force prediction. So in other words, we actually gain something, even if we're training on very tiny QM9 and MP20 systems, we actually gain some information for force prediction downstream versus just training the whole architecture just for energy and force prediction. So it means there is a sign of hope that this generative pre-training is actually learning something related to forcing, the forces related to the flow matching pre-training.
I mean, another thing that I should have mentioned is very recently, Meta has also released the OPoly dataset. Just when the community is sort of getting excited about OMOL, they drop something even bigger and better. So I guess when you have such a diverse chemical diversity that comes within OPoly or OMOL, we hope that that same diversity helps with faster convergence and better performance, especially in this MLIP setting. Because the typical issue with MLIPs is you sort of notice if you use them within downstream force fields, there's all of this stuff like energy drift, which we think could be corrected for if you train on these very large data sets.
Clear. Question on the architecture, because I don't think you guys touch much on it. Do you have anything special on the conditioning and so on, besides just like you guys mentioned, like the regular transformer, but how do you do conditioning and yeah, just in general?
Yeah, Rishabh, if you could go back to the one of the first slides for the architecture. But in general, it is actually very simple. We like if you want to think about inductive biases, it's about as simple as it gets. So it's quite literally.
Actually, sorry to interrupt, Alex. Do you want me to pull up the architecture? We have like that algorithm table in our preprint.
Oh,
you want me
that'd
to
be
pull
great.
that up?
Yeah, that'd be actually more specific.
Yeah.
But the answer is it's largely linear projections as input embeddings, and then absolute positional encodings for keeping track of which atom is first and second and third. We actually found that that's one thing that wasn't in the paper that I think maybe actually we briefly mentioned it, is that like when we try to run like more modern embeddings, like relative positional embeddings or rope embeddings on the atom indices, that actually gives us worse materials results, at least in early ablations, than if we just use absolute positional embeddings for atom indices. Something quite interesting is probably conflicting with materials representations there, which we haven't really studied too much.
And with respect to, so OMOL also gives charges and spin. Is that something that you guys condition on?
Yes. So during that, the table of OMOL results that we shared, we specifically have a set where we're keeping track of the charges and the spin features just for OMOL, so that when you pre-train or specifically when you fine-tune it for energy and force prediction, we're adding extra embeddings for the charge and spin. So yes, the model is looking at those for these results.
Okay, so you pretty much concatenated those features to like the other ones that you have at the beginning with the table.
Exactly. So you have your pre-trained trunk, you take those embeddings, and then you have some extra charge and spin embeddings, and so you just add the embeddings for charge and spin on top of the trunk embeddings.
Cool.
Yeah, thanks a lot for the very dense presentation. It was great. I still have a few questions, still related to Louis' question about the architecture, but for the pre-training losses, essentially. You said you were doing discrete masking and denoising. Do you have something that shows essentially the different parts and which one found to be more useful or not, if you have just a quick ablation or a mental map of what helped more during the pre-training?
Yeah, if you want to take this, Rishabh, otherwise I can.
Sure. Yeah. So when we have, these different modalities, we have, just to sort of do a head count, we have atomic coordinates, we have lattice angles, or like the lattice parameters in general, as well as the atomic identities. So it's like a mix of continuous and discrete data. I think taking all of these individual components together, it's just a linear sum sort of weighted differently. One could explore what it would mean to sort of add like a weighting coefficient in front of each of these different loss terms and see how much of an effect each one plays on the overall downstream performance. But of course, something like that would be pretty compute heavy. But overall, aside from this very base flow matching loss, which is like very classic that we've seen in the literature, I don't think we're doing anything, I would say, funky or extremely intricate.
Yeah, and to add on top of that, so we basically borrowed the hyperparameter like results from this previous paper called Tabasco, which had a similar setup for molecule generation. And so we borrowed their hyperparameters. So we weight the discrete losses, I think, by 0.1. So we downweight the discrete atom type losses by like 10 compared to the continuous coordinate losses. But that's basically the only tuning we're doing of the losses themselves. So discrete, in other words, we think that predicting atom types is easier than predicting coordinates. So we downweight accordingly.
And another related question is, did you have to play with the flow matching time step to make, because I guess with such a transformer, if you get very low noise level, it's tough to correctly denoise, right? Because like if you have very low magnitude, it's not obvious to correctly train on the right direction to go. And the higher the noise is, probably the easier it is to align the directions. Did you find that you had to play with the time step to make this work, or was it straightforward? And
yeah, I think Rishabh is actually at that section. So if you want to take that, Rishabh, but yeah.
No, you can go ahead. I think essentially like the main sort of point of contention is what like our, I would say, noise schedule looks like, and we kind of followed the same exact setup as ADIT for their latent flow. I mean, there's different choices. You could use like the very classic schedule for the T, just sort of sampling uniform T, or you could use some sort of cosine schedule, which is also sort of becoming popular in the community. I wouldn't say the flow matching time would inherent. I mean, if I had to sort of intuit something, I wouldn't think that the actual schedule would have too much of an adverse influence on the actual training stability or how erratic the training is. I think both of them should allow you to converge pretty decently, or at least from what we can gather from the molecular modeling literature.
Yeah.
Does that clarify?
And to add on that, and to add on that further, like once again, we looked through the literature and found what works best for like protein models and small molecule models. And so some of the best examples I've seen are like for protein, the Proteina paper from NVIDIA and La Proteina, as well as Tabasco, which was for small molecule generation. They both had this setup where they bias the time schedules or the noising schedule to like the last few time steps like you were talking about. Because it, in theory, it can be pretty difficult to predict a fully clean material from completely noisy coordinates and atom types and so on and so forth. So most of the training is happening where we bias the sampling of time steps to like, the 0.8 and higher time steps, where 1.0 is like the, clean time step, and 0.8 is pretty close to clean, but not entirely clean. So most of the training is spent near the last part of the time steps, because, you can make the argument that most of flow matching on those types of data, like molecular materials, like if it's not close to the terminal state, close to the data distribution, it's kind of meaningless and chemically invalid. So there's no use really spending too many flops trying to learn, good representations of completely corrupted chemical systems.
Another thing to note is when you are thinking about the actual downstream fine-tuning, we actually tried a bunch of things on taking the materials or the molecules and passing it through that frozen trunk. Sure, you could sort of set T equals 1 and pass the model cleanly through the architecture. But I think, and this is sort of outdated, but like, back in the day when we used to train GANs, label smoothing was a huge thing. So we also tried setting T equals 0.98 or 0.99. Instead of 1, and we saw some pretty similar performance. So from a time step embedding or what the time step sampling should look like, we wouldn't say it has too much of an influence based on some of these popular ways of doing it.
Great, thanks a lot.
Yep.
And I have one last question. I saw in your code that you at least have the adaptive layer norm like attention. I don't know if you guys tried it or used it at the end.
Yeah, that was kind of a historical artifact. So I don't think we used that by default. And that was kind of a leftover from some more diffusion transformer style architectures that we initially prototyped. So kind of how the story went is that when we kind of settled on this pure transformer architecture, we originally started with the architecture of this Tabasco paper, which is a similar setup for molecules. And we found that with a few additions of different modalities, there was a kind of a liftoff moment where we saw that the model could actually do really good materials generation almost out of the box. But there was one problem where the model was a very, very, very simple transformer, and it didn't have some QK layer norm and other niceties that people have kind of adopted in the LLM literature to improve training stability. So we could generate molecules and materials, that Tabasco-style architecture, that simple transformer, but it started running into like nans and exploding gradients if you train it for too long. And so we added some extra, basically our own what we call like modern transformer implementation of that. And in the process, one of the Tabasco authors, who was one of our collaborators, was basically showing us that like they had some ablations from the Tabasco paper where if they trained a diffusion transformer architecture, it actually gave them worse results than just their very simple transformer baseline, which was really unintuitive to test, but we kind of borrowed that wisdom here. So, in the future, we could add it back. We could try a diffusion transformer with adaptive layer norm and see if that helps. But at least historically, it didn't seem to help. So we kind of ruled that out at the beginning.
Yeah. Something else we're thinking about is what would it look like to take the transformer trunk and instead of the MLP having like an MOE layer, one can envision having experts specializing in collections of different subsets of atoms, or depending on your modality, molecule or material. Again, lots of low-hanging questions that are worth exploring, and we are exploring it with the team. That's another sort of bonus from an architectural perspective. And I think now with the Qwen 3 launch just this week or last week, Mamba style, state space models are sort of making somewhat of a comeback. So that is also something architecturally speaking, one can explore.
Got it. Thank you. I don't think there are more questions unless Ali, you have any other last questions? You good?
Good for me.
All right. Well, thank you guys. Super interesting talk. And thank you everyone for attending. Have a good day.
Thank you.
Yeah, thank you
Thanks
so
a lot.
much.
See you.
Thanks for the opportunity. Great to meet you all.